Hello viewers and welcome to a new STM32 World tutorial video. In this video we will be talking about C variables and C pointers. And let me say straight away, if you are an experienced C programmer or at least a comfortable C programmer, you might want to skip this video and watch one of the other videos in the tutorial video series. There's a nice playlist that you can pick any of them. But in an earlier video, number 19 to be exact, we were talking about C types on STM32 and that actually turned out to be one of the relatively popular videos in this video series. So it would appear that there is a need for these things. And I can understand that if you learn programming using one of the more modern high-level programming languages like, say, JavaScript, a lot of these concepts are quite confusing. But let me repeat what I said in the previous video. You absolutely must read the Bible of C programming, which is a book called The C Programming Language by Brian Kernighan and Dennis Ritchie, the two guys who actually invented C. Now, I got a few comments on the previous video. Where can I find this book? Well, you can buy it, but it is also available on the internet, so you can Google for it. Now, I don't know the copyright status of this book, so I will not point you to it, but do a Google search and you will find it. There's a GitHub repository at the moment which actually includes at least the whole text of this book. So let me repeat this. What we'll be talking about today is what we have down here in which is basically pointers primarily, but let me get back to that. As usual, I have created a new project. I call it STM32 variables, and at the moment it's just an empty project that print out a starting string there and nothing else. So let me illustrate what the confusion might be about. Now say we make a function, and I will take that function here. I made these things up front. So let's create a function which we could call inc1 for increment. And the idea being you pass it a variable and it increments that variable by 1. Now let's try this function out. And we can do that down in our main code after the starting by creating an integer with a value of 10, and we print that out and it should print 10, and then we increment by 1 and print it out one more time. Let's try to run that and see the result. And here we go. Before increment is 10, after increment is 10. So what the hell is happening here? Well, the key is that by default and by this, parameters to C functions are passed by value. And that means that when we call this, the value of all the parameters is actually pushed onto the stack, and then the function is incremented, so is executed and called. And when this executes, it will have a variable called v in here, and it will increase v by 1. But then when it returns, these values are all popped off the stack, so the v will never be passed back to the calling function. The I believe we call it down here, will remain unchanged through all this. And that is why you see a pattern sorry, one solution for this is to actually have a return value of the function. So if we try to create a new function up here, which we call int2, int2 pretty much does exactly the same. It increases v by 1 and then it returns the increased v. So let's try to execute that and see how that works out. So we have, I could write it, it's quite simple. So we now we set x, we make a variable x, and we set that x equals increment 2 of I. We could actually, now let's try to execute this. And you will see after int2, it is actually, the return value is actually 11. Now, it is perfectly legal, and we could have done it differently. We could have said, okay, we could have said I equals int2 I, and then printed out I. Simply use the same variable, but assign it the return value, and like before, it works the same way. So now I, at this point, is 11. The fact that the variables remain unchanged is why you often see pointers used in C. Now, if we imagine we do it like this instead, we create int3, and here, rather than passing a variable by value to the function int3, we pass a pointer to the original value and to the original variable, and then we increase that variable. Now, in order to call this function, we need to do that a little bit different. We can do that here. Where are we? Here. Now, instead of passing I to the increase, we pass the ampersand I, which means the address of I. Whatever address in memory the I variable is stored at, ampersand I will refer to the 32-bit address of that variable, and then that variable will be used directly. Now, since it's 11 after this, it should end up being 12 now. Let's see if it works the way we expected. And it did indeed. So these are just different way of achieving this result. This pattern of passing values by reference rather than passing them by value is an often used pattern, and we can actually make pointer variables down here. We could modify this a little bit down here and create a new variable which is a pointer to a integer, and we can define that as that. Now, this pointer will be empty at first. It won't have an address. So at first we need to assign this pointer an address, and we do that. We can set the address of the internet pointer, the IP, the integer pointer, to address of I, and then the asterisk is actually called a dereferencing. That means that this means whatever is contained at the address contained at IP, we set that to 20, and then we call the IP tree again, same function, just with the pointer. Now, this is already a pointer, so we don't need the add here. In fact, it would be wrong to give it the add. Up here, when we called int3, we had ampersand I, which is the address of I, but IP, the IP variable already contain an address, so this will work fine, and this means after we print it, that should actually be 21, since it is. So let's try to run that. and see if that works. Yes, we got 21. So two different approaches here. We pass a variable by value. Nothing is returned from this function, so this actually literally doesn't work. In ing2 it works, but the v, whatever we pass to it, remain unchanged, but we can return a value down here. And in 3 we actually modify this value directory directly and return nothing. Now this exact same approach, passing by value or passing by reference, works throughout C. It doesn't matter what we're doing. Let's imagine we define a struct. A struct is basically, you could call it a collection of variables that are bundled together. So if we have a private typedef up here, we can have a struct which contains 3 integers a, b, and c. And we can play around with this s struct down here. So if we define an s struct variable, where are we? Here. There we can define one we call s. That's why I call it s struct actually, which set the values at 10, 10, and 0. So a, b will be 10 and c will be 0. Now we can do a function that is meant to summarize a and b into c. So we could call that sum1. And let's do it like this. Now, as you can see here, the struct s is passed by value, not by reference. So in other words, if things go as we suspect, C should not be returned in any way in this case. So let's try to hang on a second, it's faster that I copy it. So let's see what we do here. After we define this s, we print out before sum1 a, b, and c, and then we execute sum1 and a, b, and c. And I would suspect that nothing is returned from this function. The struct remains unchanged. So let's see if that is the case. So before sum we had a, 10, 10, 0. After the sum1, a, 10, 10, 0. So exactly the same. So just like before, if we actually want this to do anything, we can try to return. Can we return a struct? And yes, we can. We can create this one. It takes a struct, it does the calculation, and then it returns the same struct. Let's try to execute that. So S2. Where are we? We are here. Hang on a second. So there, we define a new S2 and we call the sum2 and we set that equals, just like before, we could set S equals this, but I want to use S again. Actually, what the hell, let's do that. There's no need to do that. We'll just call S2 like that, and we will have S, S, and S. Let's see if that works. So after sum2, where we set S equals the sum2 of S, it actually returns C has been modified to 30. Now, just like before, it would be a more ever, so let's set SC equals 0 again, just to make sure. Just like before, we could do it with a pointer instead, and that will be the typical C programmers go-to way of doing this. Here where instead of passing the struct, we pass an address to the struct. This will, in this case, also be more efficient, since a pointer is only 4 bytes, rather than passing the 6 bytes we did before, where we passed it by value. Now, you'll notice in here that when you refer to a struct which is a pointer, you use an arrow rather than a dot. So C will be equals A plus B. Now let's try to call this function instead, which is our sum tree. So we add we add after this, we will have A, B, and C, so 10, 10, 0, and then we call with the address of our pointer. Let's try to execute that. And you will see that just like before, the pointer, when we pass it as a pointer, we pass it by reference, and we can modify the structures that we pass to the variable. Another thing that is logical, and this is actually what was mentioned in 78, is, and you really should go to page 78 in this manual and talking about pointer and arrays, because it's also a very important thing to understand when we're talking about pointers, and they are closely related. Let's define an array in here. So we define an array A, which contains 1, 2, 3, 4, 5. Now we can leave this empty when we define it like this. The size of this array will be 5 because it contains 5 values, but we could also put a 5 there, but let's not bother with that. Now, the arrays in C can of course be indexed like this. This is another C pattern that you might want to be interested in. If we don't know the size of an array, what we can do here is we can use the size of operator to find the memory size of the entire array and divide that integer division by the size of one of the elements. That will give us the number of elements in this array. So we cycle through this array from 0 to 5 as it will be, and we print out the actual counter, and we'll print out the value of that particular counter. Let's try to run that. It should just print 1, 2, 3, 4, 5. Here, 1, 2, 3, 4, 5. Now, the reason I show you this is that arrays are quite interesting in that we could also do it like this. We create a pointer, a simple uint pointer that points to the first element in this array. Now, if we run through this index, we can actually index this AP, even though it is not an array in itself. But if you index a pointer, it will jump up in the memory by the size of each element. So if we try that, it will print it out twice. What is interesting to see here is that if we change this to using 32-bit and change the pointer to a 32-bit pointer, it will actually work the same page. So C will know that AP points to a 32-bit 4-byte variable. So every time you increase the index, you actually increase it by 4 byte instead of, and well, it did exactly the same. There is a warning here. What is that? Oh yeah, that's because, so let's go back to 8. It didn't like that I made that a 32-bit. So let's do 8, and the warnings should disappear. Warning did disappear. That's it. So the reason why I show this is that we can actually do math with this pointer. So another way of traversing this array, rather than indexing it as an array, we can simply increase the pointer. So we go through this array again, and for each array we simply add 1 to the AP, which is, remember, a pointer to this. Now, I would originally just have written this, but it was to make it more clear, but we can do it like this. We simply increase AP for each loop, and you will see that it will now print it twice. There, one more time. So it works exactly the same. Now, this is actually where it becomes really interesting. If we make this, say, let's make it 16, so we don't get, you will see exactly the same result. So in other words, when we're talking about pointer arithmetics, when you add 1 to a pointer, you add the size of the storage element. If we have 32-bit values, it will actually add 4 byte. It knows it will add 4 byte. So the interesting part is that this will actually increase the address by 2. But if we do AP, we add 1 to AP, it will still work because C know that this is 16-bit values, so it will add 2 byte to the address of this value. That is pretty much all I wanted to say. I hope the parsing by reference and parsing by value and the idea of pointers has become a little bit clearer to you if you didn't know C. And I'll be happy if any experienced C programmers made it this far. I am actually not a very experienced C programmer, nor am I a very good C programmer, so I'll be quite happy to hear down below if I made any significant mistakes, and I might do a follow-up video later. But that's pretty much all I wanted to say in this video. As usual, please like and subscribe below if you felt that you got anything out of this video, and as usual, have a wonderful rest of the day.